Okay, and that physically looks like this requirement here. So x of y, inner product of y and z is equal to inner product of nabla x y comma z plus inner product of y comma nabla x z. Okay, and then what this is also equivalent to is that all of the parallel transport maps are isometries. Okay, so this is the key idea, is that geometrically what we want is we want our parallel transport structure to preserve the inner product. Okay, that way when we parallel transport two vectors, their angle is preserved. Okay, so really we want the parallel transport structure to not just be an isometry of the tangent spaces as vector spaces, we actually want the parallel transport structure to give us an isometry of the tangent spaces as inner product spaces. Okay, um, and when we require that, it's equivalent to requiring that this covariant derivative of the metric tensor vanishes. Okay, and it turns out that you can show that there is a unique connection for any Riemannian manifold. There is a unique connection which satisfies this torsion-free property, so the Hessian is symmetric, and the metric compatibility. Okay, so the parallel transport structure forms an isometry of the tangent spaces as inner product spaces rather than just vector spaces. And so if we require these two conditions, namely metric compatibility and torsion free, what we end up with is a unique connection, and we can prove this connection not only exists but is unique. So the proof of existence, there is a way to prove existence, which is essentially using the Whitney embedding theorem. You embed the manifold into Rn, Euclidean space. You can show that Euclidean space, or actually you need I think a stronger embedding theorem. I think you need like the Nash embedding theorem or something. I think you need to isometrically embed the manifold into Rn. Let me just double check this. Okay. Yeah, so we actually need a Nash embedding theorem because we need to use the fact that any Riemannian manifold can be embedded into the standard Euclidean space isometrically. Okay. Yeah, so using that fact, we can embed any manifold into Euclidean space isometrically, and then we can essentially define a covariant derivative using the covariant derivative of Euclidean space, which just has vanishing Christoffel symbols. That's a Levi-Cevita connection for Euclidean space, is the vanishing Christoffel symbols. Okay, so then we can just define the covariant derivative on the Riemannian manifold as just the projection of the Euclidean covariant derivative, the Euclidean Levi-Cevita connection. We project that onto the tangent bundle of the manifold. Okay, so similarly to how we discussed previously, right? The covariant derivative is just the projection of the directional derivative in the ambient Euclidean space onto the tangent bundle. It turns out it's actually a very special that's actually a very special type of covariant derivative, in the sense that if the manifold is isometrically embedded into the Euclidean space, then this way of defining the covariant derivative by projecting the ambient Euclidean covariant derivative, which is just the Euclidean directional derivative, if you project that onto the tangent bundle, that actually gives you the Levi-Cevita connection for your manifold, which you can prove is unique. And there's two different proofs of uniqueness which use explicit construction. Okay, so essentially, if you calculate the torsion-free condition in coordinates, okay, then you're going to get that this torsion-free condition, which is a coordinate-free condition, right, setting the torsion tensor. The torsion is a tensor. The torsion tensor is given by t of xy is equal to nabla xy minus nabla yx minus the bracket x comma y. Okay, so the commutator of x and y. And so that's the torsion tensor. It's a coordinate-free description because it's a tensor field expressed entirely in terms of the connection and the commutator of vector fields. Since the torsion tensor is obviously coordinate free, but we can find a coordinate based. We can find a coordinate um, equivalent condition for torsion-free and coordinates, and this is that the Christoffel symbols are symmetric in the bottom two indices. So remember, the Christoffel symbol is defined by if we take our if we take a coordinate vector frame partial I of the manifold, then the Christoffel symbol lambda superscript L subscript ij is equal to essentially the Lth component of the covariant derivative of um, the vector field ej, or partial j, in the direction partial I. Okay, so that, let me just state this explicitly. We have that nabla of ej in the direction ei, so nabla sub partial I of partial j is equal to lambda superscript L subscript ij partial subscript L. Okay, so right. So that's basically the definition of the Christoffel symbol. Is it's lambda L sub ij is equal to the Lth component of, in the basis partial I, of the covariant derivative of E sub j with respect to E sub I. Okay, or I keep using E. I'm sorry, I keep using E. I should be using partial, because we're not using an orthonormal basis necessarily. We're just using the coordinate basis. So let me just say that one more time. Lambda superscript L subscript ij is the Lth component in the basis partial I of the covariant derivative of partial j in the direction partial I. Okay. All right. So where was I going with this? Well, yeah. So if you calculate the setting the torsion tensor identically equal to 0, which is equivalent to requiring the Hessian is symmetric, then you can show that that's equivalent to, in local coordinates, these Christoffel symbols being symmetric in the bottom two indices. So namely, lambda L ij is equal to lambda L sub ji. Okay. Okay. So now, right. So if you calculate in terms of the Christoffel symbols, this torsion-free condition, and then you add the condition that it's also metric compatible, okay, then you can use if you add the condition the metric is also the covariant derivative is also compatible with the metric. Okay, so we have that since it's torsion free, the Christoffel symbols are symmetric in the bottom two indices, and then it's also compatible with the metric. Okay, then we can use an algebra to basically solve for the Christoffel symbols explicitly in terms of the metric. We can solve for the Christoffel symbols explicitly in terms of the metric, and this is a very um, um, this is an argument that you'll see in every differential geometry class. It's a coordinate-based proof, but it basically explicitly constructs the Christoffel symbols in terms of the components of the metric. Okay, and this is essentially done by taking first-order derivatives of the metric. These first-order derivatives of the metric can be expressed in terms of Christoffel symbols summed over the metric, and then um, and then we can using this argument we can essentially solve for the explicit form of the Christoffel symbols. So since the Christoffel symbols are entirely determined by the metric and these two conditions of torsion free and metric compatibility, we're going to get the existence and uniqueness. Okay, and the existence proof actually follows by using some sort of partition of unity argument, and like a local existence proof. Just look at this argument on paper. So we take the partial derivative with respect to I of the jkth element of the metric. This is by definition the metric evaluated on partial j partial k, and then we use the metric compatibility here to bring this partial derivative inside. Okay, so this is just a vector field, right? This is a vector field. So by the metric compatibility of the connection, This is given by the product rule here. Okay, well, but by definition, these covariant derivatives of the basis vector fields with respect to a different basis vector fields, that's just the that's just a new vector field whose coefficients are the Christoffel symbols. Okay, so we end up with the Christoffel symbols here and here in both arguments, and then of course we can factor out the Christoffel symbols due to the linearity of the metric by linearity of the metric, and so then we get an explicit form of this first derivative partial I of gjk in terms of the Christoffel symbols. Okay, and right, and so now we do that similarly for, we just shuffle the indices around in an appropriate way. We shuffle the indices around, permute the indices, and then we get this formula, which basically we can use to cancel out, to solve explicitly. Like, we can cancel out all the Christoffel symbols except for the specific lambda L ij. Okay, so we can isolate for this term lambda Lij, cancel out all the other Christoffel symbols. And then and then we can just take the inverse of the metric here and solve for the Christoffel symbols explicitly. So this is the formula for the Christoffel symbols, which of course are of the Levi-Cevita connection. So these are the Christoffel symbols which determine the Levi-Cevita connection, not any connection. So this is lambda Lij is equal to 1/2 G superscript Lk of partial J Gki plus partial I Gjk minus partial K Gij, where again these superscripts here are this is the inverse of the metric tensor. Okay, so it's the inverse. Okay, so this proves uniqueness, and then also, but there's a really nice proof which is coordinate free. Okay, so the second proof of this, the existence and uniqueness of the Christoffel symbols is the coordinate free description, and it essentially involves just shuffling around the torsion free and the metric compatibility in a ton of cases, and you can think of this almost as equivalent to like a, if you were doing integration by parts almost. I don't know if you've done one of those problems where you have to integrate by parts like twice or maybe 3 times, and then you end up with, after you integrate by parts enough times, you end up with the integral that you started with, and then you just subtract it over or you add it over to get a formula for the integral. That's what the proof of solving for the inner product of that's how we solve for the inner product of nabla xy comma z in terms of just the metric, so the inner product, and and the bracket, so the commutators. Okay, so it turns out that if you do enough product rules and enough juggling, which I'm not going to cite out explicitly this algebra here, but if you do enough of, if you take the covariant derivative, apply the, in this first, let's just do 2 lines. So this first line here, right, where we have nabla xy comma z is equal to x of the inner product yz minus the inner product of y nabla xz. So this is just metric compatibility, right? This is just the metric compatibility of of the um, of the Levi-Cevita connection with the inner product. And the second line, we replace nabla xz with nabla zx plus the commutator of x and z, and that's the torsion-free condition. Okay, and so then whenever we end up with a whenever we end up with a covariant derivative, we're just going to apply either the metric compatibility here or the torsion-free condition. And if you do this, like, you know, over and over again, there's like what, 1, 2, 3, 4, 5, 6 lines here. Then you can end up with the original. You can get back to where you started and end up with an expression which only contains only contains inner products and commutators of vector fields, and then one term which gives you the same covariant derivative as what you started with. And so you can just add this over and get that you can characterize this, the inner product of nabla xy with any z, where x, y, and z are arbitrary vector fields. You can fully characterize this inner product just in terms of um, the inner products of the vector fields themselves. So x inner product yz minus z inner product yx plus y inner product zx, and then minus inner product of z with the commutator of y and x plus the inner product of the commutator of z with y and x minus the inner product of y with the commutator of x and z. You can see the right hand side here is just entirely determined by the metric. The left hand side you can use to entirely characterize the connection. And so you can see that the Levi-Cevita connection must be determined by the metric. This formula is called the Koszul formula. I'm not sure how to say this. Koszul formula. And if we just take these vector fields, these arbitrary vector fields x, y, and z to be partial I, partial j, partial L, just the coordinate vector fields in local coordinates, then we reduce to this formula for the Christoffel symbols in terms of the metric in coordinates. Okay. All right, and then note that actually this formula, this Koszul formula, actually gives us a way to literally define nabla xy. Okay, so we can just use this as the definition of nabla xy, and then it's once we define it to be this way, then yeah, we're done. We've constructed the Levi-Cevita connection. So since we've constructed it explicitly, construction which is fully determined by the metric, that automatically proves uniqueness, right? It automatically proves uniqueness because we have an explicit construction of what it must be. It's kind of the best possible way to prove uniqueness. Okay, so is that everything I wanted to mention? Yeah, that should be good for now. Yeah.